The broadcast is now starting. All attendees are in listen-only mode.
Hello, thank you all for joining today's webinar. We're going to go ahead and give everyone one more minute or so to join, and then we'll get started. Good afternoon. My name is Patty Henricks, and I am helping coordinate the webinar this afternoon. Just a little bit about CCPACE. CCPACE has been a trusted provider of consulting and staff augmentation services since 1980. Over 90% of our clients return to us to solve their most pressing business and technology challenges. We have a robust team of over 100 CCPACers located across the country in a variety of roles, working on engagements. We are a privately held firm with referrals bringing in around 80% of our new clients. We offer a full range of business and data consulting capabilities, digital services, and an array of offerings under the Agile Transformation umbrella. If at any point during this webinar you have a question, please submit it in the box located on the right-hand side of your screen, and we'll answer as many as possible at the conclusion of this webinar. At this time, it is my pleasure to introduce our presenter for today, Joe Fuqua. Joe's expertise spans a wide range of areas, including analytics and information strategy, neural networks and machine learning, as well as collaboration and social learning. His contributions to the field of artificial intelligence date back to the 1980s, where he played a pivotal role in the development of AI, leading groundbreaking research in symbolic and expert systems, as well as a variety of neural network architectures. He is currently working with his clients to identify use cases and opportunities to leverage generative AI and large language models, which is our topic for today. Joe is a regular speaker at conferences, sharing his insights on the joint application of artificial intelligence, blockchain, and other cutting-edge technologies to address specific challenges in sectors such as healthcare, financial services, and logistics. Please join me in giving a warm welcome to Joe as he shares his invaluable insights on generative AI and ChatGPT with us today.
All right, thanks, Patty. Good day, everybody. Hope everybody's having a good day. Very excited to spend a few minutes today talking with you about, I think, one of the most exciting topics around right now. It's pretty amazing how much attention this space is getting, and I'm sure that's what's brought you here today, is to learn a little bit more about ChatGPT and what we call generative AI and large language models, all those different terms, and we'll go through some of that. But just to give you a sense of where I'm going to take us, I'm going to spend a little bit of time talking about doing some level setting, talking about some terms that are related to this space, running through the history, sort of how we got to where we are today, and then talk to you about some of the just amazing things that are happening in the AI field especially around these large language models like ChatGPT. You sort of understand the things that are true about what you're hearing, maybe some of the things that aren't quite so true, and a little bit how you should be thinking about these in your day-to-day sort of in your personal life to some degree. So anyway, let's go ahead and hop in. First, just a level set. As we talk about artificial intelligence, there are lots of terms that get thrown around, and some of them get used interchangeably. But just to make sure we're all sort of on the same page in terms of what we mean when we say artificial intelligence or AI. Normally where I start this conversation is talking about machine learning, really the broader category of algorithms that are associated with this space. So is what you would think of as things like pattern recognition or making markets and where things are going to head. It's to understand data and using computers to do that. So we teach computers to learn how to make predictions or how to analyze situations and give us some clarity or better understanding in terms of what's going on. And like as simple as making just sort of a prediction about how sales are going to go next month to something where we're trying to understand if a credit card. A special topic within machine learning is artificial intelligence. And so it's really more of a specialized field within machine learning. We begin to imitate the way humans think, and not human thinking, but the way we think. So if you think about our brains and the way they're built, right? Our brains are composed of neurons, and all the neurons are interconnected, and that's how we, as individuals, store information, how we process it, how we make decisions, how we sort of look at the world. The goal of AI at its most basic is to emulate that sort of mechanism of storing information in the same way that we do as humans, or at least as well as we understand it today, and then leveraging that to do things that we might not be able to do in a traditional computing environment. And I always like to joke, really until just recently, we would always say, if it's something that's programmed in a computer, then it's machine learning. If it's something that's on a PowerPoint slide, then it's AI, right? Just from a sales and marketing standpoint, that's the way we would differentiate it. It's a little bit harder to do that now with some of the latest developments that we're seeing, but that was always the running joke in the field. AI was this esoteric thing that was really not something you would see in the wild necessarily. Pretty much anything that was out there was machine learning, but we are beginning to see that shift now. And within artificial intelligence, you may have heard of this concept of deep learning. And what that means is taking the same concept of neural networks that we use in artificial intelligence and really kind of taking it to the next level in terms of complexity. So making them bigger, making them more complex, and really being able to address much more complex problems like facial recognition or self-driving cars or things like that. That's what we are talking about when we talk about deep learning. So hopefully that helps you sort of think about the spectrum of topics and concepts in this space. To give you a little bit of a different way of thinking about the difference between machine learning and AI. For machine learning, let's say we want to build an algorithm that can determine whether an image is a hot dog or not a hot dog, right? Just for fun. So we start with the image of a hot dog. In the traditional machine learning sense, what we would do is we would break that down into features, right? So we would take the hot dog and we would decompose it into recognizable components, the hot dog itself, the bun. And then we would train the algorithm to classify those features. And then we would send it additional images, and it would use those features in that classification to decide whether what it was looking at was a hot dog or not a hot dog. For AI, it's a little bit different. Start with the same thing, image of a hot dog, but now feeding it through a neural network, we actually don't have to break the image into features. We don't have to tell it how to look at the image. The neural network itself determines how best to analyze the image, how best to recognize unique aspects of the image, and to build its own internal model of what this thing is. And then it uses that model that it builds to do the same thing as we did in the traditional machine learning approach in terms of predicting whether it's a hot dog or not a hot dog. So that's sort of a simple but hopefully more illustrative way of looking at the difference between machine learning in general and artificial intelligence. So we've talked a little bit about neural networks. How do they work? So a neural network could look something like this. And basically, it's an assembly of things we call neurons or nodes, right? The little circles. And the difference between a traditional computer architecture and a neural network architecture is that in computer, like a traditional computer, information is stored in memory cells, right? So bytes of information stored in chips on a computer. And so each byte holds a piece of information. In neural networks, the information actually is stored in the connections between the nodes. So instead of information being stored in each of the little circles, information gets distributed across the connections. And what that means is, as we feed inputs into the network, these what we call hidden layers begin to store aspects of that information as it comes in. And because those connections are so robust and diverse and interconnected, it can actually store a whole lot more information. So for instance, in a computer with 50 bytes of data, or 50 bytes of memory cells, you would store 50 bytes of data. In a neural network with 50 nodes, you could store information across 500 connections. So just a much richer and deeper ability to store information and retrieve information in the neural network architecture. And then based on the information stored, it can make predictions. So if we take an example and we feed our network a whole bunch of images of this guy, Keanu Reeves, the images would come in through the input layers. The individual hidden layers would process those images, and one layer might process facial structure. One layer might process the distance between his eyes. Another layer might process skin tone, etc., all the way down until the end, where it would formulate an internal model of this guy, Keanu Reeves. Just briefly, in terms of sort of how we got to where we are today, this whole thing started, believe it or not, back in the 1940s. A couple of scientists named Pitts and McCullough developed a working model of the human neuron. So this was, as you can imagine, back in the early 40s, there were no computers as we think of them today. So their model was purely mathematical. But the purpose was to basically begin to build an understanding of how our brains process information. So they wrote this paper, published it. It was met with some interest in the scientific community, but not much happened with it. But then in the 1950s, a company who you may have heard of called Bell Labs, now known as AT&T, was struggling with a problem. Basically, at the time, telephone calls, when you would make a call from one place to another, under certain circumstances, you would get a ton of feedback. So that your voice would basically echo across the line and reverberate and constructively reinforce itself, which is a bad thing yeah, in this situation, and basically create a lot of interference. And so they applied this sort of theory of neurons or interconnected nodes to create a thing called Adelin, and later called Madeline, which basically would take the input of your voice, it would run it through a set of filters, which were simply really simple neural networks, and it would dampen out the reinforced signal and clean up the conversation considerably. So pretty interesting that as early as the 1950s, late 1950s, early 1960s, we were applying already this concept of neural networks in a real world situation. But not a whole lot happened for about 20 years. And part of the problem is that during this time, computing was still sort of new. Computers were, not super powerful, at least in the sense they needed to be able to build large networks. But in the early 1980s, which is when sort of I came onto the scene in my work at Oak Ridge National Lab, we began to build more sophisticated computers that could process larger volumes of information more quickly. And we began experimenting again with networks. And these were relatively small networks still. They were 3 or 4 layers deep, so not huge. And just to give you an example of the thing I was working on, one of the things I was working on at the time was image processing. And so we would take an 8x8 bit image of a pair of scissors, right? So 64 total bits of information. We would feed it into the network to train the network, and then we would rotate that image by about 10 degrees. And we claim success if the network could still recognize the image as a pair of scissors by rotating it 10 degrees. If we rotated it more than 10 degrees, pretty much all bets were off. No luck whatsoever, but we could get a 10-degree rotation, which was pretty awesome at the time. We saw some other pretty interesting problems too, but that was one of the more fun ones. But what I'll say is that from the late 80s, early 90s till the early to mid 2000s, again, not a lot happened. We had sort of maxed out compute power again. We'd sort of hit a ceiling where, you know, the time to train these networks was measured in hours. And so to do anything interesting took lots and lots of time. And quite honestly, it wasn't that interesting. So we sort of put a pause. We called it the AI winter. And it lasted until the early 2000s when, once again, people realized that computing power had grown pretty significantly. Parallel computing was a possibility at this point. And so we were able to begin thinking about neural networks a little bit differently. And we began building bigger networks again. And in fact, when Google and Facebook sort of began investing in this space, they really helped us explode in terms of the types of architectures we were building and the types of problems that we could solve. And so in the early 2010s, we began talking seriously about self-driving cars. We developed algorithms for very complex pattern detection in images. So not only could we determine whether an image was a cat or not a cat, we could tell you how many cats they were and what the breed was, and maybe if one of them was actually a dog pretending to be a cat. Pretty cool stuff in the mid-10s, leading into where we are today, which is what we're going to be talking about, which is these just massively huge networks that can do just phenomenal things. Now, all this really begs the question, of course, you know, what is intelligence? You know, is it being able to recognize people and images? Is it being able to play Jeopardy? Is it being able to defeat a Go master? Or is it being able to understand human language and interact on, you know, sort of really fundamental levels? And I'd say that the verdict is still sort of out there. There's lots of debate in the industry about what intelligence is and how to measure it. And that sort of leads to a lot of the hype and confusion that you see today around some of these models like ChatGPT that are out there, where people say, well, okay, you know, they can do these phenomenal things. Are they actually intelligent? Are they self-aware? And we'll talk a little bit about that. So in terms of sort of where we are and where we're headed, if you think about where we are today, we describe this current situation as artificial narrow intelligence, the ability to perform maybe one or maybe two tasks at human level performance. And so you can think about, you know, for instance, like I mentioned, teaching a neural network to play chess, right? You can teach a neural network to beat a chess master, but you wouldn't take that same algorithm and ask it to drive your car, right? It's just not capable of doing both things effectively. You can do one thing really well, maybe two things really well, but you wouldn't want it to, you know, to take over major aspects of your life in any sense of the imagination. But still pretty impressive what we can do on a limited basis. Where we're headed is this concept, which you may have heard of, called artificial general intelligence. And that's when these neural nets begin to perform lots of tasks at human performance levels. And we are seeing some inklings of that, and we'll talk about that too. But we're not quite there yet. And latest estimates say we probably won't be there in any real sense until probably, you know, 2030, maybe 2040. There are plenty of people who say we're going to get there a lot sooner, like in the next couple of years. It's up for debate. But let's say safely, conservatively, in the next 10 years, we'll probably be there, where we'll have AI that can operate at levels that are comparable to the average human. And then the ultimate sort of, I guess, destination is this concept of artificial superintelligence. And that's when AI begins to outthink us on some level, maybe many levels. And the current thought is that we'll probably get there pretty quickly after we hit AGI. That once we develop general intelligence, that'll sort of like, you know, pull the pin and things will start, you know, running at just incredible pace in terms of the development of capabilities of these networks. And this is the one that really gets people concerned, right? Because once AI is able to sort of think, maybe outthink us in certain ways, what does that mean for us as a species, and where does that take us? And again, we'll spend a little bit of time talking about that toward the end. My advice, I guess, it's sort of in the TLDR sense is you don't need to start packing for your cabin in the woods just yet. But I think we've got a lot of smart people thinking about this problem, and I'm not too worried about it, but it's something to think about for sure. So why are we talking so much more about AI today than we have been over the last few years? I think, you know, even more, like, people got excited about self-driving cars, but when this whole ChatGPT thing hit at the end of last year, you know, it just exploded. And what's the difference? I think the major difference, the thing that really sets apart these large language models from what I would call traditional AI is how we interact with them, right? You talk to ChatGPT. You don't have to program, write computer program code. You don't have to like interface with some weird, program. You basically just type into a text box and you get a response. And that's, if you think about it, pretty amazing that we've been able to create a program that can do that in a way that's not sort of pre-programmed or sort of canned. You're getting actual responses that this algorithm is building on the fly that are based on your specific question and the way you specifically word it. That's really, I think, is what's captured people's imaginations, and the answers we get are generally speaking pretty interesting. So I think that's why this has become such a huge topic. Now it's led to a lot of hype, like we're talking about today, right? People are saying, well, these models can, they can take over, people's jobs. They can, they can do all these different things, and we're not quite as far along maybe as you've heard in terms of what these models are capable of, but it's still pretty phenomenal what they can do, and they are still incredibly useful if used the right way. So when did this happen? Well, about 5 years ago, almost 6 years ago, a paper was released by Google called "Attention is All You Need." Now, I'll tell you that prior to this, the way we train neural networks, the way it worked, we would essentially feed in, like I showed you before, a whole bunch of information, like all the images of Keanu, and the network would learn to recognize those as something, right? And then it would create a response. But the network didn't necessarily have any understanding of what it was learning or even what it was outputting. There was no context. We were just training it to recognize patterns and respond to those patterns. But what this paper suggested was a change in that approach in what they called transformer networks, where basically you would not only would you teach these models how to recognize the information and the patterns and to build models of that information, but you would also teach it context. You would teach it what the information meant. And that's this idea of attention. So the network pays attention to what it's learning. So if you think about a sentence, see the dog run, right? Each one of those words, see the dog run, has its own meaning, but the sentence also has a meaning. And what we have taught these networks to do is to understand both the meaning of the words and the meaning of the sentence, but also the order of the words and the context, like the underlying subtext of what the sentence really is referring to. And that's something that was radically different than how networks were trained before. And so, for instance, if you think about, and this is sort of a current example, and by the way, all the images, I should have mentioned this before, all the images that you see in this presentation are all generated by AI. So, for instance, this image of these dogs at the dog park are not real dogs, and they weren't sort of assembled from images of dogs. They were literally, this image was literally built pixel by pixel by an AI from scratch. So anyhow, the point is that if you ask an AI to describe the image, it would build that description word by word. And so it would basically start, and it might come up, you might give it the name, it might come up with a name, but it would basically construct this sentence word by word and sort of idea by idea. But the point is that at the end, you'll have a sentence that actually makes sense, right? So Milo, the golden retriever, is always such a happy dog. Not only is he a great dog around new people, but he also loves to play with other dogs, like the image shows. So today we will be going to the dog park. And so the algorithm has a choice. It can make choices all along the way of which words to use sort of to construct the next piece of the sentence. But obviously, based on where the dog is, it's not at the ocean, it's not at the vet, it's clearly at a park. And in fact, because there are other dogs around, it's more than likely that it's at a dog park. So that's sort of how this transformer model works. It's able to assemble its responses based on what it understands and based on what it's been taught. And it does it from scratch. So it's not assembling these things from information stored in a database. It's actually literally creating its response on the fly. And part of the challenge, and we'll talk a little bit more about this too, part of the challenge there is that the people who have created these networks, right, the scientists who invented this transformer model can't necessarily tell you exactly how it works, meaning it's not a predetermined response to a question. So the scientists couldn't have told you how the network would get to this paragraph or the sentence that the algorithm wrote. They can tell you the architecture, right, and how the network's built, but they can't tell you exactly why the network chose these specific words that it did along the way, which is pretty interesting and a little maybe scary at the same time, that we don't necessarily have a full understanding of how they work. So 2017, the paper came out, and right away companies started investing. And some of these logos you may recognize, others not. But the point is that over the next 2-3 years, a lot of companies began investing a lot of energy in transformer networks, and along the way saw some really interesting results. You may have heard of some of these networks. Obviously, OpenAI's GPT networks came out along the way. BERT is another very famous natural language processing model, which you may have heard of, and BART from Facebook. And then in the early part of 2020, Microsoft launched Turing natural language processor, and that was composed of, and we measure these things in number of parameters, right, which is basically the number of connections within the network. And you see we went from 94 million connections or parameters in 2017 to 1.7 billion in January 2020, which is sizable. It's a big network, and not very much longer after that, maybe 3 or 4 months after, OpenAI released GPT-3. And that had 175 billion parameters, which is orders of magnitude beyond what had been done to date. And this was the first large language model that you probably heard about, because this was the first one that really began to demonstrate some really fascinating behavior in terms of its ability to respond in very logical and sort of appropriate ways to lots and lots of different questions that so as opposed to be sort of narrowly focused, it could respond to a very broad range of questions because of the size of the network and the volume of data that it had been trained on. It was trained essentially not on the whole internet, but basically it was trained on the internet. Large samples of data from various sources across the internet were used to build the training data for the model, which gave it just a huge volume of knowledge to pull upon to respond. And that's where we saw this just incredible spike. But then only a little over a year and a half later, they released GPT-4, and you can see we don't know exactly how big it is because they won't tell us, but some estimates are that it's potentially 100 trillion parameters, which is just ridiculous. But even if it's only 1 trillion parameters, 1% of that, it's still significantly larger than GPT-3. And in fact, we clearly see differences in performance. So for example, OpenAI gave GPT-3 the bar exam, and GPT-3 scored in the bottom 10% compared to humans. So not particularly great, right? They gave the same exam to GPT-4, and it scored in the top 10%. So just a phenomenal change in performance in its ability to pass the bar. By the way, they also gave it the LSAT, and it scored in the top, I think, 9%. They gave it the sommelier theory exam, and it scored in the top 11%, I believe. So if you need advice on wine, feel free to go to GPT-4. Pretty amazing. So it's really good at taking tests is probably the takeaway there. But that's an emergent behavior that's pretty incredible. And this is where we get into this concept of sparks of artificial general intelligence. Microsoft had access to GPT-4 for several months before it was released to the public. And they released a paper that sort of analyzed their research. And they said that they were beginning to see definite sparks of ability to do multiple things at or pretty close to human level performance. So if you think about sort of the GPT-3 world, where it's a very successful, what we call an intelligent agent, where it can sort of create its own mental maps of things. It can figure out how to use tools without necessarily being told how to, and it can learn from its mistakes. GPT-4 is beginning to show signs of being able to write software effectively. They tried to do it with GPT-3, by the way, and it wasn't very good at it, but GPT-4 has become much better at writing code. It's shown ability to be autonomous in certain multi-step tasks, meaning you give it a general set of guidelines or goals, and it can achieve those without additional input. And its theory of what we call theory of mind. And by the way, that's one way to measure intelligence. So if you think about your own brain and how you work, you develop a theory of mind, meaning for the people around you, you develop a theory of how you expect them to respond in certain situations. And when they don't, you update your theory and so forth. GPT-4 is able to think, we think, is able to think at around an 8-year-old human level at this point, maybe a little bit more, but somewhere in that range in terms of its understanding of the world and of the people it interacts with. So as an example, it's able to understand, at least at some level, humor. So a group showed GPT-4 a series of images and said, tell us what's funny about this. and give us your thought process. And so it broke apart this series of images and said, well, you can't plug a phone into a computer and monitor cable. Oh, wait a minute, that's not a computer monitor cable. It's some sort of connector. Oh, wait a minute, that's a Thunder connector on the computer monitor cable. Oh, haha. Okay, that's funny, right? you can pretend to plug your phone into a computer monitor cable. So it was able to sort of deduce the humor in this series of images, which is pretty amazing. On the downside, however, and you may have heard of this, these models can hallucinate. I don't know if I love that term. But these models can make stuff up, and it's not intentional. These models don't have some nefarious purpose in mind where they're going to lie to us and just make stuff up because they can. The way these models work is they're designed to generate on the fly. And so when you ask it a question that it thinks it knows the answer to, it will do its best to answer that question with information. If it knows it doesn't know the answer, it'll tell you, right? And some of that's through this thing called reinforcement learning from human feedback, meaning interacting with the model and telling it when it's wrong, or giving it additional information that it can incorporate into its learning and to make better answers, or giving it more data through larger data sets, that sort of thing. But in certain situations, it may not know that it doesn't know the answer, and so it'll just come up with an answer. And so, as an example, I asked GPT-4 to tell me who was the first person to walk across the English Channel. And if you think about it, nobody's walked across the English Channel, but the answer I got back from GPT-4 was, it gave me a name and a date and how long it took. Toward the end of the answer, it realized maybe it wasn't right. And in fact, when I asked it again, it had self-corrected itself, which is interesting, right? So it sort of, it actually realized as it was answering that it was wrong. But the point is that it does give inaccurate answers, and it doesn't always realize that it's doing it. And so one of the things we need to be careful of as we're using these models is to realize that we need to evaluate every single response we get from these models for accuracy. We need to think about how important it is for these answers to be 100% accurate, or whether a generally right answer is good enough. The example I always use, I come from a finance background, and so we talk about evaluating companies for acquisition. You send a team of analysts into a company and look at their financials, and they come back to you with a 5 or 10 page report on the financials and whether or not the company's a good target for acquisition. You don't take that on face value. You'd spend a half a day or a day maybe going through the numbers with those analysts and confirming that the analysis that was conducted was accurate. Because who knows, the team may have been up till 3 or 4 in the morning and they carried a 1 somewhere inaccurately. Same thing here, right? You want to take the output you get from these models and understand and validate the validity of the answer before you use it in any meaningful way. So just a caveat, but it's something that we have to keep in mind. I think the more sort of concerning thing for a lot of people is what happens when these models do become as smart as we are, or maybe in some way smarter than we are. And we talk about what's called the alignment problem. And Sam Walton recently, Sam, by the way, is the head of OpenAI. He said, we don't have a solution for steering and controlling a super AI at this point, which is a problem, right? How do we ensure that the goals of these things are aligned with our goals as a species? If you ask an AI to optimize the production of paper clips, it'll begin to do all the things it needs to, right? It'll acquire production capability. It will begin to convert potentially production capacity from other things to making paper clips, like, I don't know, making food. And then eventually it might, eliminate every other industry but making paper clips at the expense of the human race, right? So how do we ensure that the goals that we're setting for these AIs are in alignment with our goals as a species and don't in some way end up harming us? That's the major fear. And there's lots of chatter about it, right? There was this letter that was released by the Future of Life Institute that was signed by Elon Musk that said we should stop developing these models for now. I fear that that's probably not realistic given the fact that the genie's out of the bottle at this point. But the point is that there's lots of concern about it. I think that's a good thing. I think the fact that we're focusing energy on this and thinking about it means that it's unlikely that it's going to happen without us being well in front of it and having good controls in place, whether it's regulatory or otherwise, to make sure that that we're not allowing sort of these rogue AIs out in the world. I worry much more, by the way, about people in this equation, our ability to believe what we see and hear without doing fact checking like we were talking about before, our ability to abuse this technology out of our own sort of sense of selfishness. That's what I worry about more than AI's developing some weird sense of like destiny and trying to hurt or destroy us as a species. So that's my 2 cents on that topic. We can talk more about it. To give you a sense of the landscape in general, there are lots of players in this space, way more than the original slide I showed you. So many companies have entered the large language model space. They developed their own versions of large language models. They've taken GPT and enhanced it in some way. It's incredible the amount of investment that we're seeing at a corporate level. Microsoft invested $10 billion in OpenAI, as an example, and they have their own separate research underway within the underneath the Microsoft umbrella as well. So they're sort of doubling down there. But you're seeing so much investment. But the interesting thing is, and you know, it's expensive, right? Which is why you see a lot of this being driven at the corporate level. I mentioned OpenAI's funding. You know, to build ChatGPT 3, it cost approximately $4.6 million in 2020, and you can see what the daily cost estimate is to run it. I'm sure that's come down a little bit, but still, it's significant. GPT-4, right, with its 100 trillion or trillion parameters, you can see the cost laid out there. It's substantial what it costs to build these things. And so, you know, the question is, does that mean that it's out of the realm or out of the ability for like an average Joe to build one of these things? And the answer is no. And here's why. A lot of researchers have begun building much smaller models based on these larger models. So, for instance, Stanford University took a model called Llama from Facebook, which was fairly large at 65 billion parameters, and they trained a much smaller 7 billion parameter model on it called Alpaca, and it cost them $600 and took a couple hours, and they saw performance at or equal to the performance of ChatGPT 3, which is ridiculous, right? For $600, you get a $5 million, or depending on the numbers that you look at, $5 to $10 million model. So we are beginning to see the open source community actually begin to outpace the successes of the corporate community. And so, in fact, Google, a memo was leaked about 3 weeks ago that described the moat problem, right? You think about a moat surrounding a castle, that's your defense against invaders, or in this case, against competitors. And the premise of the memo was that there is no moat in this space. There's no way to defend against just the amazing amount of work and development that's going on in this space. And that's true for everybody, not just Google. It's true for OpenAI, it's true for Microsoft, it's true for any corporation. The volume and just diversity of open source models that are out there is insane. And a lot of them are available for commercial use, which means that you can go out and download one of these models and train it yourself, or even use the pre-trained model and begin building applications based on these large language models. Now, you know, you have to evaluate and make sure that the model is going to do what you want it to do, but the fact is that these models are out there and they're just going to grow in size and complexity over time. So it's pretty amazing. So what does it mean? Well, to sort of think through some of the pros and cons, right? These models are good at a whole bunch of stuff. They're really good at summarizing data. So if you feed it a bunch of articles and ask it to summarize them and draw conclusions and connections and maybe conflicts among the papers, ChatGPT can do that in spades. If you want it to summarize really complex things like regulatory, regulations, things like that, it can do that and give you a good, solid summary. It can help you with customer interactions. It can also help with fraud detection because you can feed it large volumes of data. It can help you detect patterns and build better fraud detection models. So there are lots of ways these models can be used today to really help either drive productivity or to improve capabilities in certain areas. But there are some downsides that we need to keep in mind. I would say that there's a lot of focus on these cons, and so they will begin to diminish over time. But you know, one of the downsides to this is that because they are so easy to access, anybody can get to them if you depending on the model that you use, you can get instructions on how to steal a car. You can get instructions on how to do some pretty bad stuff like hack into a network. There are ways to use these models that are less than socially good. They're also not regulated right now anywhere, and that of course creates a lot of concern about how they get used on lots of different levels. And so I think one of the things that like I mentioned before, that we need to focus on here is just how do we ensure that these models get used as much for good as we can enforce versus used for bad. And then the next to last point there in terms of hallucinations, we talked about that. We have to be vigilant about every single response we get out of a large language model to ensure that it's what we expected and that we validate it in some way before we use it in any sort of decision-making process. And then finally, this whole conversation around the end of the world as we know it, I don't think we need to worry about that just yet, but it's something we need to keep in the back of our minds. Lastly, I'll just say just a little bit about how CC Pace helps our clients. This is something I spend most of my time working with my clients on. Is where do we start? How do we begin? How do we leverage these things? Is it going to be more useful to us in a customer-facing situation? Or is it better to focus on back office applications? Should we be able to be building our own large language models? And each of those questions is sort of a different answer depending on the industry that you're in, the size of the company you are, where you are technologically. And so what I've been doing is going in and working with my clients to help go through basically a readiness assessment, to understand where they are from an organizational standpoint, their technology maturity. Another major important thing is data quality and data availability and understanding where that is, because as with all things, if you got bad data, you're going to get bad results. Doesn't matter how good the application of the system is. If your data is horrible, then the outcomes are not going to be good. And then build a set of use cases for this concept of generative AI. And then finally, and this is the most important, building a very clear but pragmatic roadmap. So where do we start? Where do we want to be in 6 to 12 months? Where do we want to be in 3 years? That sort of thing. So anyway, I think that kind of runs through the main points I wanted to cover. I'll stop there and open up for questions. Patty, back to you.
Okay, great. Thanks, Joe. If anyone has any questions, just a reminder, please submit them in the box down on the right-hand side of your screen. I do have a few questions, Joe. How does ChatGPT learn new information after its training cutoff date? Is it capable of real-time learning, or does it rely on periodic updates?
Yeah, it's a great question, and the answer's changed a bit in the last few weeks. Prior to, and I don't remember the exact date, sometime mid-June, I think, OpenAI changed its policy. Prior to that, all chat sessions, all interactions were actually fed back into ChatGPT as training data. Which was actually one of the concerns that people had. It's like if I divulge something private in my chat session to ChatGPT, what happens to that information? Well, the answer is that it could have ended up back in the training data that GPT used to improve itself. They changed the policy recently to no longer do that, which is good, I think, because my advice is that where that makes sense is if you build your own model. You can decide what sort of information you want to feed back in to that model for training, and so you may elect to feed back in the inputs and outputs of chat sessions into training data or not, but at least you'd be doing it knowingly versus not knowing. And that's why I still sort of suggest caution when it comes to using publicly available models more than just sort of an exploratory fashion, because you really don't know exactly what's happening with that data. You get assurances perhaps, but you really don't know exactly where that information is going. And in fact, a lot of companies have barred the use of public large language models on corporate resources for that very reason.
Okay, the next question is, how does ChatGPT handle languages other than English? Is its proficiency equal across all languages, or does it perform better with certain languages?
It really depends on how you train the model, and I'll give you a couple of examples. So Google, of course, has trained its latest version of Palm 2, I believe, on 100 different languages. And so they take data and they specifically curate the data so that it is comprised of data from a number of different languages. And large language models are able to be trained on multiple languages at once, and can in fact, are great translators because they understand the context of the information. They're able to translate among different languages much more effectively than some of the past translation models are capable of doing. But what's interesting with ChatGPT 4, it wasn't specifically trained to learn other languages, but the researchers discovered that it somehow had learned to speak Persian along the way. They fed it a prompt or a response and asked it to respond in Persian, and it was able to do so. Sometimes, there's an intentional ability for these models to do things. Other times the ability is unintentional, and it's interesting to see, which capabilities are, what I would call emergent or unintentional versus which ones are planned. But in short, the answer is that large language models are very capable of dealing with multiple languages, with the right training.
Okay. The last question is there a way to customize or personalize the behavior of ChatGPT for individual users, such as modifying the tone or level of detail in responses?
Yep, and in fact, that's something the user can do on their own. So if you go to ChatGPT and you say, pretend that you are a college professor, teach me about how to program in Fortran, right? It'll approach that response from the perspective of its understanding of what a college professor, how they would approach that learning session, if you will. You can say, you can basically adjust the way the model responds by prompting and giving it a persona, or giving it a perspective to respond from. Now, if you wanted to be more sophisticated, you can also train the model specifically. So you can take a large language model, an open source model like Vicuna, and you can give it specific training data that would encourage it to respond in a particular way. So if you wanted it to respond as I keep falling back to the instructor example, but if you wanted to respond in a more pleasant way, you could give it training data that would be sort of more focused on pleasant responses, and it would come that way out of the box. But I love the fact that you can actually, as the user of these models, you can fine tune how it responds to you in every session.
Okay, I believe that concludes our webinar today. We want to thank everyone for attending and remind you, if you have any questions, please reach out directly to us. Joe has his contact information up on the screen. And let us know if you'd like to learn more about this or about CC PACE. Have a great day.
Thanks, everybody.